Today we will be taking T-notes on conduction, convection, and radiation. These are the three ways that heat or thermal energy can be transferred. The first way that energy can be transferred through thermal energy is through conduction, which is when there is a transference of that energy into the particles. And then from those particles, those collide with each other, and therefore the heat energy is able to transport itself from point A to point B. There are certain materials that allow heat to be transferred more easily, and these are called conductors. One type of conductor is metal, and this is why we use cookware, because cookware allows heat to transfer from the heat source into the pot, into the foods that we're trying to heat up. Okay, so we're going to watch this simulation, and what this is showing is that your hand is over here and you're holding a glass rod. And so if you can imagine, the molecules within the glass rod look like this, and here is the heat source. So you have your hand holding a glass rod that is nearby a heat source, and we know that this area where the heat source exists is going to excite the particles on the end that is closest to that heat source. And as those particles get heated up, they become more and more excited and start to act more frantically and more erratically. And as those particles start to move more and more, that excitability bounces off onto the nearby molecules. And so eventually what you will notice is that more and more of the molecules are going to become more excited. As that excitation occurs, then what you will eventually see is a transference of energy, and you should feel that the glass rod becomes hotter and hotter. So we mentioned that metals are good conductors, and within metals there are different kinds of metals, and I just wanted to show you that within the category of metals, not every metal is created equally or can transfer heat as well as another. So from the top here we have silver. Pure silver is the best conductor for the transference of thermal energy. Some of these metals are very expensive. There's not a lot of it. It's difficult to get, and therefore we don't use them for various things such as wiring in our housing or for even our cookware. Back in the past, they actually used to use silver in the wiring, but that got very expensive. And so now we've gone down to copper, which we at the time had a lot of access to, and it was much cheaper. And if you just look down here, you'll notice that there's various other materials that could be used for conducting energy. Where do we see conduction in the world today? Well, one example is for fenced wires. And with fenced wires, what we notice is that they expand in the summer and then contract in the winter. And so over time, with this expansion and contraction, fences start to become loose and saggy, and you have to keep up with it. You have to maintain the fences. We also see this with power lines. So with overhead power lines, they expand in the summer again, and again in the winter they contract, and so these also start to drag down, and so you get these droops that have the wiring going down closer towards the road. And everyone has probably experienced this. The creaking of a house throughout the day is due to the expansion and the contraction that comes from the sun hitting the house and then expanding the materials that the house is made of. So we talked about conduction, we talked about conductors. Now we can talk about materials that do not conduct heat very well, and those are called insulators. These do the opposite of a conductor. They do not allow the molecules to become excited. They don't allow heat or thermal energy to pass through them. So these are air, wood, plastic, cork, wool. There are various other kinds of insulators. These are just some examples. And another thing to note is that the more layers that you increase of these insulators, then there is more air that can be trapped. And so that can help us when you're trying to stay warm, for example. Convection is the second way that thermal energy can be transferred. And this is when we have the movement of particles from one place to another. This only happens in liquids and gases. So, for example, we have a boiling pot of water, and we have heated particles of the liquid rising, while colder particles of the liquid sinking, and then as the colder particles are going down towards the heat source, they get heated and then they bubble up. And so you get this twirling or swirling of cold and hot particles, which creates this current, and this current is called convection. We also see this, remember, with gases. And in a house where you have a heat source, you have your heat going upwards towards the top of the house and then coming down towards the colder area. And remember that the heat, when the hot particles of air move upwards, it pushes the cold particles down, which then goes towards the heat source to get warm. And so then you get this circulation of hot air and cold air. We also see this in smaller pockets, but all around the Earth. And so we have these compartmentalized sections of cold air falling down and hot air going up. And so we get these pockets of wind currents. And so this is where convection is also occurring, and it's happening all over the Earth. Here we have a kettle that is heating up water, and as you can see that as the heating device here is heating the particles of water, it pushes the hot particles of water upwards, which then displaces the colder particles of water down to get heated, which then creates this convection, this movement, this current of hot and cold. Again, this is why we're able to see currents in the ocean, and that's because of the sun coming and hitting the Earth at such a way that it heats up the water more at the equator, which then sends the heated water downwards towards the colder areas, thus displacing the colder areas into the area where it would then get heated again by the sun, thus creating pockets of hot movement and cold movements of water. Thermal radiation is the third and last way that thermal energy can be transferred. This is called electromagnetic radiation, or EM radiation. We've already studied this in our energy unit, so this is familiar to you. It is energy that is carried by heat, and heat is given off by all objects, all living animals, humans, hot and cold objects. Now, hotter objects emit more radiation, and one thing to note is that thermal radiation radiates in all directions. So even though you see the sun here with the sun rays emitting to the right towards where Earth is, the sun is also emitting rays outwards this way and also towards you, into your eyes and away from your eyes on the back side of the sun, which we can't see. We call thermal radiation infrared radiation, or IR. It does not need a medium to travel through. This is how we're able to get radiation from the sun to the Earth. So it can travel through a vacuum. Thermal radiation can be absorbed by objects, it can be emitted by objects, or it can be reflected by those objects. So here we have all three being shown. We have the sun that is shining onto the Earth, and some of that is going to be absorbed. And so the Earth itself, the water, the land, the air gets warm. But then some of this solar energy gets reflected back. And that comes from hitting the ozone layer. It could also reflect off of the clouds. It could reflect off of the water. And then we have that the Earth is emitting the energy. So there is some of the energy that is being absorbed. And then, of course, it's going to release some of that energy. And that energy is going to be released out of Earth's land, air, and then released into space again. Here is something that you might remember from having studied energies and the types of energy, and when we were talking about EM spectrum. So this is just to remind you that there are different kinds of wavelengths of energy that is within the electromagnetic spectrum. So we have conduction, convection, and radiation. Sometimes you might actually see this happening within the same event. So for example, For example, we have convection where the air is rising to help heat this person's hands. At the same time, here we have the heat going into the metal rod, which would then be the action of conduction. And then over here we have radiation, where the light heat is hitting this person's hand and therefore transferring that energy to also warm the person. So all these three types of transfers of energy can be happening at the same time. Here again is another example where we have all three, convection, conduction, and radiation happening at the same time. We have radiation, and so you would get light, energy in all directions, and that is radiation. We also have convection because the particles of air are getting heated and then moving upwards and outwards to areas of cooler temperature. And then we also have conduction because here we have the heat that is going to be exciting the molecules of the wax, and then the wax molecules will then change from a solid into a liquid. And so therefore we have conduction. So here is where we can see all three forms of energy transfer happening at the same time. Now, what surfaces are best for reflecting radiation? You guys have already showed that you understand that shiny surfaces and light surfaces are really good for reflecting. Okay, so shiny light-colored surfaces reflect a large portion of radiation. They do not absorb a lot. So here we have incoming radiation, and then when it hits the shiny surface, it reflects. The surface only warms up a little bit, so this is why when you're in a hot area, you want to wear light-colored clothing. Now, surfaces that are best for absorbing radiation are going to be your dull, dark-colored surfaces or materials, because those absorb a large amount of that radiation and then they reflect very little. Because so much of the radiation or the heat energy is entering into the surface, then that surface is going to heat up very quickly. And there's a little bit of radiation that is reflected, but not very much. And so this is why we're able to see dark hair feels hotter in the sun versus lighter hair over a certain amount of time. One thing is true about materials that absorb or reflect radiation is that objects that are good absorbers of radiation are also good emitters. So for example, if you have a dull dark color, we know that those are going to absorb fast. They're going to get hotter faster, but they're also going to cool faster. So they're going to emit the energy just as quickly as they did absorb it. Same thing here. A shiny or light color is going to absorb slowly. It's going to reflect a lot more of its heat, but then it's also going to emit that heat or release that heat slower than that of a darker color object. Therefore, it cools slower. Now, surface area affects an object's ability to radiate heat. And this is really important. The more surface area that an object has, then the hotter it will be because it can absorb much more quickly. It's getting a lot more contact with that thermal energy. And therefore, it's also going to be able to cool faster because it has more surface area on which that heat can be released from. Likewise, if you have a smaller surface area, it's going to be less contact with that heat source, so you're going to absorb slower and you're going to emit slower. All right, we've reached the end of our video T-notes. If I went quickly, review by just going back and rewatching any of the videos, look over your notes, make sure it makes sense, and be ready to use this information in class. Thanks for watching.